Hi, my name is Neil and I would like to demonstrate my honors project for you where I attempt to identify StyleGAN generated images. The title of my project is Identifying StyleGAN Images. My supervisor for the project was Dr. Rudy Serfontein. Dr. Rudy guided me throughout 2021 and helped me in completing the project successfully and professionally. Special thanks to Prof. Tiny Dutoy that inspired me in the field of artificial intelligence and always was available to aid me with any questions that I may have. Prof. Tiny also let me make use of his graphics card for the option I study. The problem this project aims to address is the newly released Generative Adversarial Network StyleGAN that can create images of human faces that are accurate and may not even be detected by real humans. Fraudsters can use StyleGAN generated faces as part of false identities. The detection of such images with the use of artificial intelligence will be useful in the growing cybercrime world. In 2019, Facebook took down an undisclosed number of fake profiles that use StyleGAN generated profile pictures to establish false identities on the internet. StyleGAN was developed and released by NVIDIA to the public in December 2018. It uses a generative adversarial network to create images by applying styles, for instance glasses, brown hair, and gender features, on images to morph them into newly generated human images. Here we can see the styles from the source image being applied to the newly generated image. StyleGAN 2 improved the GAN so that the artifacts that were noticeable in the initial release were no longer present. StyleGAN 3 was released in October 2021. The newest version of the GAN exceeded expectations, and NVIDIA realized the possible problems the GAN might cause the general public. NVIDIA therefore also teamed up with forensic scientists to develop detection methods for StyleGAN. In this demonstration, we can see a comparison between StyleGAN 2 and StyleGAN 3. StyleGAN 3 has no artifacts and dataset noise and can also synthesize realistic hair features. Because of the time of StyleGAN 3 and 2 releases and the increased difficulty in detecting StyleGAN images, the scope of this project will only focus on the detection of StyleGAN version 1 generated images. The problem of StyleGAN generated faces aiding in the malicious creation of false identities was demonstrated in the crackdown of Facebook profiles and in NVIDIA realizing the problem StyleGAN might cause. A method to detect these images is required. In this project's literature study, it was identified that a machine learning deep neural network approach will be the simplest solution to the problem. A deep learning approach will require the use of a convolutional neural network, or CNN for short. CNNs are commonly used in computer vision applications because of their exceptional ability to extract features from images. A CNN achieves this by breaking down images into small kernels. On the right is a representation of how the network might extract features from the StyleGAN dataset and classify them. The contribution this project aims to add to the artificial intelligence world is a method of detecting StyleGAN images that can aid average people to detect whether the profiles they see are real people. This project can also be used by fact-checking entities in the news space and also by law enforcement battling cybercrimes. For the completion of the artifact in this project, the design science research methodology was followed in combination with Agile. Agile allowed for the workload to be broken down into manageable sprints, and each sprint was a small period handling a specific problem. The sprint structure of the artifact creation consisted of an initial sprint where a neural network was created and the datasets used was processed. The second sprint saw the training of the neural network and the evaluation of the success achieved in training. In the third sprint, the new emerging technology, Optina, was used to optimize the neural network. And in the final sprint, the Flask framework was used to create a front end and implement the final model. Now that we have a clear understanding of the problem and method of detection, let's explore the neural network that was created. The neural network model initially created used hot and cold learning techniques for optimization of the network architecture. The model takes on RGB images with a resolution of 200 pixels by 200 pixels. The model consists of 7 deep convolutional layers, and the activation function used on the convolutional layers are the ReLU function. The final layer uses a sigmoid function that allow the model output to either be 0 or 1, indicating StyleGAN or real human images respectively. To classify the images between StyleGAN and real images, large datasets had to be used for training. The flicker faces in StyleGAN dataset each contain 100,000 unique images. From that, we use a subset of 10,000 images each. Both of the datasets allowed for the use in this project as stipulated by the respective licenses. While processing and training the dataset, it was found that identifying StyleGAN images takes a lot of processing resources. Image classification neural networks need graphic processing in the form of GPUs instead of conventional CPUs. In this project's processing resources was a big obstacle. With no GPU available, Google Colab's free online Jupyter notebooks were used with a GPU, in combination with the GPU provided by Prof. Tiny. When training with the original StyleGAN and Flickr Faces dataset, the training times would be too long. In Google Colab, a notebook can only run for 12 hours and notebook processing power is throttled. Training the neural network with 200 pixel resolution images reduced the training times drastically and impacted the accuracy slightly. With the base neural network architecture and a proof of concept, the next step was optimizing the neural network. Instead of using hot and cold learning, Optuna was used to optimize the neural network with hyperparameter tuning. Optuna uses machine learning to determine what is the best hyperparameters for a neural network to maximize its accuracy. The Optuna model with a 97.6% real-world accuracy consists of a total of 37 million trainable parameters. The Optuna model consisted of 6 convolutional layers, 2 pooling layers, and 2 dense layers. The optimization came in the form of better dropout rates and the number of parameters in each layer. Optuna improved the model's accuracy from 70% to 97%. With the neural network trained and optimized, the next step was to implement the model into an application that people can use. For the front end of the artifact, the Flask framework was used. Flask is based on the Django framework and is a lighter version that does not need an elaborate backend. The advantage to using Flask is that it is Python based compared to React and Angular that is JavaScript based. The neural network model can be implemented in the front end manager script, meaning there is no need for APIs or added complexity to the implementation. When a user uploads an image to the application, the process also prepares the image so that it can be passed through the neural network. After the image is uploaded, it is passed to the neural network model, and the model returns the probability and if the received image is a StyleGAN or real human image. The user will see the label the model gives the image and the model's confidence in its prediction. Now I will demonstrate the working artifact that was created based on all the information in the video. The main page of the application provides the user with a minimalistic interface with clear instructions. The user can upload an image to classify using the control. For user-friendliness, a 404 page, or rather a page not found landing was implemented to guide the user back to the home page in the event of misbrowsing from the user. Similarly, if a user uploads the wrong file or no file at all, an error page is presented with clear instructions. For the demonstration, let's upload an image. This is a StyleGAN image that the model has never seen before in training. The neural network correctly predicts that this is a StyleGAN generated image. Here you can see an artifact. Again, the model predicts with 100% confidence that this is a StyleGAN image. This is a human image. Let's see if the model can detect it. The model predicts with 99% accurate confidence that this is a real human image. This not only works with the Flickr Faces and the StyleGAN dataset, but also works with images retrieved from lecturers at the Northwest University. Let's try Dr. Rudy's image. The model predicts with 100% accuracy that Dr. Rudy is a real human image. Again, the model predicts with 100% accuracy that Prof. Tiny's image is a real human image. But let's investigate why the model misidentifies images sometimes. StyleGAN images all struggle with creating realistic backgrounds when generating faces. When a real image with a standard unclear background is passed through the model may misclassify the image. Image resolutions that do not have the same width and height may also be misclassified due to morphing and not being able to pass through the input layer. On the left is a comparison of the self-created model and the Optina optimized model. Now, let us compare all the models that was created. The results of the neural networks are as follows. The self-created neural network model presented a validation accuracy of 81.7% and tested to present a 70% real-world accuracy. The Optina optimized model presented a 97.3% validation accuracy and tested to present a 97.6% real-world accuracy. This shows the success achieved by implementing hyperparameter optimization using Optina on our neural network model to detect StyleGAN images. This project aimed to identify StyleGAN generated images. By evaluating StyleGAN and possible solutions to the problem, was a convolutional neural network identified as the simplest solution to the problem. Hyperparameter optimization was used to improve the model. The model's accuracy improved from 70% to 97% when identifying StyleGAN images. The optimized model's problem is that when it makes an incorrect prediction 3% of the time, it is overconfident in its wrongful identification. The detection of StyleGAN images was accomplished. The successful implementation of the neural network in an application that allows for the identification of StyleGAN images was created.